Research is hard. Probably everyone watching right now experienced this at some point, and this series of videos is intended to make following recent research in the world of vector addition systems even just that slight bit easier. This video specifically is part 2 of a 7-part series about the GVAS reachability problem. The videos should be watched in sequence. In particular, in this video, we assume that part 1 has been watched. We now also assume some familiarity with vector addition systems, though no details like the reachability algorithm, etc. With that out of the way, let's dive straight in. So, GVAS reachability explained 2. Today we're going to talk about almost linear grammars, a concept I will define in a moment. So first, let's repeat a little bit what we did in the last video. So in the last video, we saw that essentially in order to create a reachability algorithm, we need 3 parts. We need a sufficient condition for reachability. We need pumping cycles, one of the parts of the sufficient condition, and we need a difference cycle, the second part. Well, this will become clearer in a moment when we actually see how the sufficient condition looks like, because we will of course be repeating this. And then last time we saw the sufficient condition for top branching, and today we are going to look at the 3 red parts. So we are going to look at all 3 parts for almost linear. In particular, after today's video, you will be able to write the reachability algorithm for almost linear grammars. Okay, so first, the table of contents for today is a reminder of the algorithm. And, well, the algorithm just looks so nice. It sounds like the matrix, a wonderful thing. I always like to call something the something. It's well, and then step 2, we're going to define almost linear. Then, well, we need a new sufficient condition for almost linear. We will see at that point why we need a new one. We're going to define the well-founded rank, and then finally we end by defining the procedure simple of G. Well, this, again, simple of G becomes clear now with this slide. So this was the sufficient condition from last time. And the algorithm, again, the same as last time, is the following. Just observe that this time I have actually fixed the problem. And the algorithm starts by taking our favorite grammar, the one we want to decide reachability for, and then it's going to check whether there exists a valid path. Just to remind you what was a valid path, well, a valid path had 3 conditions. It was supposed to start and end at 0 to the d. It's supposed to be derivable in the grammar. And it's supposed to remain in n to the d. So it's not supposed to go negative. And the path with just the first 2 was called a z-run. And this is irrelevant because it's always going to be in the condition that there's supposed to be a z-run. But existence of a z-run is easy to decide. Okay, so with this out of the way, let's again look at this algorithm. So we want to decide reachability. How do we do it? Well, we have a sufficient condition, and what are we going to do? Well, we're going to check whether the sufficient condition currently holds for everything in the workset. If the sufficient condition holds for everything in the workset, then the while loop ends, and we return whether the workset is empty or not. Namely, if the workset is non-empty, then we know that there is a valid path because the element of the workset fulfills the sufficient condition. Remember, we have exited the while loop. So the only thing we need to be able to do is we need to be able to take something from the workset, decide the sufficient condition. For this here, this is not remotely easy like for this condition, but for almost linear grammars, this will not be as much of a problem. And then, assuming that the sufficient condition does not hold, we want to create smaller grammars. And then we update the workset by removing the current grammar and inputting the smaller grammars. Okay, so what's an almost linear grammar? An almost linear grammar is defined as follows. A grammar is almost linear if every production that does not leave the current SEC is of the form A goes to W8 prime W prime. So let's first see what does it mean leave the current SEC. So for example, this production here leaves the current SEC. In what sense does it leave the current SEC? Well, in the sense that there is no symbol on the right hand side. There is no symbol on the right hand side which is in the same SEC as the left hand side. So like nothing here is in the same SEC, is not in the same SEC of S. And so in particular, because the above only states something for rules which do not leave the current SEC, what we have is that any acyclic grammar is almost linear. In particular, this first grammar is a positive example. But now you might have already looked ahead and you might have seen the second example, and here I say this is a non-example. Why is that? Well, this is a rule which does not leave the current SEC. In fact, it produces literally the same symbol again. But it is not of the form A goes to W8 and prime W prime, because here there is another non-terminal in addition to the one in the same SEC. Okay. So with this out of the way, let's talk about another important thing about almost linear grammars. This is something I touched on at the start of the last video. But in almost linear grammars, we usually want this tree-like structure. We want to distinguish between the left exit of the, so if a rule leaves the current SEC, then we want to distinguish between the left non-terminal of this rule and the right non-terminal of this rule. So we want to distinguish between this blue and this green non-terminal. Here this will be the green non-terminal and this will be the blue one. And now this we do by having non-terminals remember where they came from. Well, this makes the grammar exponentially larger, but this is not much of a problem. Like in VASS reachability, we have bigger problems than exponential blowups. Okay, and then the second one I already said, this is not almost linear. So maybe as an intuition for what is an almost linear grammar, and another reason why I described this, an almost linear grammar is kind of a tree-shaped vase. Well, in a very strong sense that every SEC, since it has only words here, every SEC is a vase. Every SEC is literally just an SEC of a vase. But the structure of the SECs is not a linear structure, but rather the SECs are sorted in a tree-like fashion. Okay, and at this point you are going to wonder, okay, why do we look at this weird notion? Has anybody even defined this? So, first of all, I can tell you this has been defined before in the literature. So, in 2015 there was a paper on coverability in one GVAS. So I know that Leroux was one of the authors. I think Soutré was another one. Good question whether there were any more. Well, you can check it. It's called coverability in. Is it one-dimensional pushdown vector addition system or GVAS? Well, anyways. You can find it, and they define this concept, but that's not actually the motivation. The motivation is an exercise I gave last time. Specifically, I last time gave the exercise of what happens if you take a grammar and you enforce that production P and P is used exactly m times. Okay, what happens if you do this? Well, if you do this, then what I claim, so first of all, how do you implement this? Well, you would start with the non-terminal Sm, where essentially this number up here remembers how often you still have to use the production. And then whenever you have a rule S goes to Ss, well, you split the k between I and j, where importantly then of course you want to have I plus j equals k. Okay, and now what does this become as a grammar? this is actually the motivation for almost linear grammars. Because if you do this, what happens is, first of all, there is like a part of the grammar that is, you take your original grammar and you remove p, but then what's on top of it is an almost linear grammar. So let's look at why is this the case. So the point is, if you look at the non-terminals S0, then this is exactly going to produce, this is exactly going to be your original grammar with the production p removed. And then if you look at these rules, sk goes to si sj, what can we say about these rules? Well, here, this is where the interesting thing happens. Well, we can distinguish two cases. So if both of them are greater 0, then this means that this leaves the current SEC. So since it leaves the current SEC, this is it does not have any influence on being almost linear or not. However, the interesting case is, what if I equals 0? Well, if I equals 0, then this means you have a rule that says sk goes to S0 sk. What this means is you have like a part that is an almost linear grammar if you view this green part as being a terminal. So it's exactly like a kind of grammar where below you have your original grammar with p removed, and on top of it you have built an almost linear grammar. Importantly, what you built on top is not a linear grammar, because of course you had this exception here. This would accept you from being a linear grammar. But that's the point. It's an almost linear grammar. So this is exactly the motivation for this. Like, if you want to do this kind of decomposition, and I can tell you we want to do this all the time. Taking a production and say it used exactly this often, we want to do this all the time. If you want to do this all the time, then you want to say that, well, removing a production from your SEC and in exchange throwing something almost linear on top makes your grammar easier. But in order to say this, well, we have to really understand almost linear grammars very well, and this is what today's video is supposed to do. So most introductions to GVAS would kind of skip over almost linear grammars, but I think this is one of the aspects you have to understand why this is actually simplifying your object and not like making it more complicated. Okay, so let's start with our analysis of almost linear grammars. In particular, let's start with, why does this sufficient condition from last time fail here? So this is the sufficient condition from last time. Just to remember, what was the point? The point is you have something that does s goes to delta s minus delta prime. So this is called a pump. Well, and I already write it like this. Of course, strictly speaking, this derives some word and not actually just delta, but like I'm trying to simplify the proof here. You can imagine this is just delta and delta prime, like just one letter that does plus delta or minus delta prime at the end. And then this is called a pump, because if you apply this, then your target, because you view your target as moving backwards here, your target does plus delta prime. And well, on your source, it's obvious you do plus delta, so you go here. And now what happened is both your source and your target became larger. And if you make your source and your target larger, intuitively the query becomes larger. Now the problem is that delta and delta prime are not equal, and this is exactly going to produce the problem here. Consider this example here. S goes to plus 1, S minus 2, and S goes to minus 2, S plus 3. And now first of all, let's check that this condition is true here. So here, what do we have? Well, this is a stereotypical pump. Like, it could not be much clearer that this is a pump no matter what I do. This is the most basic pump you could have. And here, what do you have? Well, this is a difference, I claim, a difference derivation, a difference cycle. In what sense? Well, what was the condition that we want on this? well, this is the cycle here that says the effect, if you sum all these effects of the left and right hand sides of these two cycles, then you're supposed to get 0. So let's check whether this is actually true. So live arithmetic, +1 -2 -2 +3. This indeed equals 0. Well, actually I didn't have to do the arithmetic. I know that I chose the example correctly beforehand. Clever preparation. Well, but the more interesting thing is, I claim that this does not have a valid path. Why is that? Well, essentially the first rule, well, you are allowed to borrow yourself X euros, but at the end of the derivation you then have to pay back 2x euros. On the other hand, you are allowed to pay somebody 2y euros, and in exchange you are going to at the end get 3y euros. And now your run has to be greater than or equal to 0 here when you did all the borrowing, when you did all the left hand side, and it has to be greater than or equal to 0 at the end. So let's check these two equations. Well, the first equation is x minus 2y, or inequalities, not equations, is x minus 2y is greater than or equal to 0. And the second inequality is 3y, sorry, that's exactly the point. It's not just the right hand side, but it's the full sum that is supposed to be greater than or equal to 0. If we sum all of this, then we get y minus x. This is supposed to be greater than or equal to 0. Okay, now what can we do with inequalities? Well, we can sum them, and then we know that they're still true. So if we sum these inequalities, then we get, okay, x cancels out, and we get minus y is greater than or equal to 0, which, well, is a contradiction. Or, okay, math purists could now say, well, y equals 0 could still be a solution, but well, the point is y equals 0 will not work either. You can then plug this back in and you get a contradiction as well. Okay, so there is no solution here. This means that there is no run. Okay, so what was the problem? Well, the problem was that you have to explicitly talk about this before this S and after this S. So there is a clear before and a clear after. And, well, kind of the inequality should have talked about this before and after. But here, when we talked about this effect, we completely ignored this. Yeah, so let's try to repair this condition. Well, first of all, let me give you a condition that is very simple, but that would do the job. So if you have two cycles, both of them are pumps. So the first is S goes to delta S minus delta prime, and the second thing is S goes to delta prime prime S delta prime prime prime. But importantly, you have this condition here: the sum is equal. Then I claim that this actually works. So why does it work? Well, if you put these two cycles there's a minus here. If you put these two cycles together, then you get S goes to delta plus delta prime prime S and minus delta prime minus delta prime prime prime. Okay, I literally just composed the two cycles. This is just a composition of the two cycles. Okay, but now what's the point about this one? Well, we can use the condition here. These two sides, like this here, this is exactly, this here equals minus the right hand side. Or the sum of the two sides is 0. What this means is, okay, if you think you want to go from 0 to the d to 0 to the d, now if you apply the cycle, you want to go from delta plus delta prime prime to delta plus delta prime prime. Well, you had dashes, you had like one more dash here. You had here delta prime plus delta prime prime prime, but these are equal. So you can write here delta plus delta prime prime. And now this means that you just answer the question whether you can go from 0 to 0 is equivalent, is like induced by the question whether you can go from the larger thing, that is delta plus delta prime prime, to delta plus delta prime prime. And importantly, this is greater than equal to 1D and this here as well. And now by doing this often enough, you can make any Z run into an actual run. Like this, the point is the left and the right hand sides of what you did are equal. Because the left and the right hand sides are equal, when you do this reduction, you still ask for a run from 0 to 0. This was different in this situation. In this situation, if you apply the pump, then afterwards you want a run that creates more effect. Like you just produced an effect of -1 in total. So if you apply this pump, then afterwards you need to cancel it and produce more effect. This is not the case here. Here you afterwards have to produce the same amount of effect. This is why in this case actually you are fine. Okay, so of course you realize probably that I could have also written this condition as there is a cycle with left and right sides equal. Yeah, that is another option you could have done. But that would be really a very difficult to check condition. It's already difficult enough as it's written here. Okay. But let's see how else could we repair this condition? Like how can we make it more general? Because this is too restrictive. Well, consider this example here. S goes to +1 S and minus A, where A is some number. And S goes to -1 S and plus A plus 1. Again, A is the same number. Okay, what's the point? Well, if you think about it, this is like borrowing money with a ratio of -A. Borrowing money with a ratio of A. And this is like paying it back with a ratio of A plus 1. And, well, the point is A plus 1 is greater than A. And we will see in a moment that this becomes relevant. Well, actually not in a moment, we will see this immediately. Because by composition I get the following thing. Well, I simplify it slightly, like I'm just talking about the effect. You can make this precise, don't worry. You get, if you compose these, a cycle that says S goes to 0, S, and then 1, or +1. And now the point is, if I plug this composed cycle together with this guy, oh, okay, I guess you actually cannot see this. I have to... Ah, okay, this barely worked. Okay. Okay, but I should not be writing here. Okay, if you compose these two, if I compose these two enough times, then I get S goes to +1 S -1. And now I'm in a situation from before. Well, one of the reasons why I wrote the condition with this double cycle thing before and not just with one cycle is that, well, it's easier to see that if you have this ratio situation, then you can produce this double cycle thing. Like, if you have the ratio situation, you can produce the cycle thing. It's not obvious, but you can do it by like appropriate combinations. So if you have this, cycle thing and you have a better ratio for paying the money back, then in fact you have a valid path. Okay, but this is still not general enough, and we need to still generalize it slightly. And this is something that, well, I was told that Ranko Lasic was one of the first to coin this term, but like whoever invented it, it's a very clever term, the borrow-invest scheme. And what does the borrow-invest scheme do? Well, consider the following grammar. So I like to visualize this as I have S here, and then I have two A1s, one on the left and one on the right. As always, I want to distinguish between the left and right child. And now here S, this has a ratio of, like here I can borrow money with a ratio of 3. Okay, so why do I say this is a ratio of 3? Well, if I have a pump that goes S goes to plus A, S minus B, then I say the ratio is B over A. And well, here I made it easy and assumed A is 1, then it's just at the right hand side. Okay, so ratio B over A. How does this ratio, well, the question is, do we have a run here or not? I claim that in this case here for this grammar, we can in fact do the lifting stuff all, again exactly as in this lemma. Well, differently than in the lemma, but it works. Why? Well, what you would do is you borrow yourself a ridiculous sum of money here, call it X. Now you go into your first child here with money X. You apply this rule. What does this do? Well, you can do it as often as you have counter value, because this has a minus 1 on the left, so there's a limit on how often you can do. You can do it at most x times, but then at the end you have value 2x. Now with these 2x, you go to the right child, and also in this child you can double, and you end here with the value 4x. Now you're here at the start of this SEC with value 4x, and so what's going to happen is at the end of this SEC you still have value x left. Now you might say that x is too much, but if you just don't double fully, but you double a little bit less, like by just going to epsilon earlier, then you can make sure that you actually end up at the correct value. So also in this case, you have a run. And so now you might ask, okay, this was one-dimensional. I mean, here I can see it. I just borrow money with a certain ratio and then pay it back. But you promised me a solution that works with arbitrarily many counters. Yeah, this is what we're now going to define. I'm trying to set the stage and put this intuition first to tell you, to give you a good intuition for what's now going to happen, because the formal condition is not as easy. So the formal condition uses what is called an ILP, or integer linear program. I assume that you are familiar with integer linear programs. Well, it's not a complicated thing. You can also think of it as linear equations over n. Like, it's literally just linear equations over n. Over n is important. This is actually where the difficulty of linear programming lies. If you have linear equations over z or q, that's in p, but linear equations over n are difficult. Okay. So, let's look at this example tree. Well, it's a tree we had a lot of already, and now, well, it's going to serve to illustrate what the ILP is going to do. So first of all, an ILP needs variables. So what variables do we have? Well, the main variables are these. Okay, what just happened to the tree? Well, the tree has now 4 situations. It has these inputs, and it has these outputs always. Or this is how I view it. You have a left input and a right input, and then you have a left output and a right output. Because what you're kind of trying to do is you're kind of trying to say, okay, I want the cycle S goes to W S W prime, and I want to describe what these words here are doing. So these words here in VASS terms, they are supposed to move you from the left one from x epsilon to x epsilon prime. And the right one is supposed to move you from y epsilon prime to y epsilon. Or I like to think of this backwards. Your target originally was y epsilon, but now afterwards the target is y epsilon prime. So like, you think of it as building a context, and the context, like what you describe, is for both sides of the context, the input and the output of the corresponding word in VASS terms. And this will be what these variables here are describing. And now, of course, you don't just have these variables in one SCC, but you have these variables in every single SCC. So also here you have these variables, also here you have these variables, and so on. Okay, that's the first thing. ILP needs variables, but the second thing is an ILP needs equations. So let's define the equations. Well, okay, maybe first this intuition. If you like think back to this borrow invest scheme, like what I wrote here with this x, 2x, 2x, 4x, and then 4x here and x, this should remind you of the variables I'm now writing. Like this is what you should have in mind now for the variables that I'm writing. This scheme of that the money wanders around the tree. Like you borrow yourself X at the top SCC, then you do something in the lower SCCs and you put it back at the top. This is what you should have in mind for this now. Okay, but so let's formally define the equations. So we're going to distinguish between P. P is a position now, not a production. Position meaning it's a word over left, right. So, well, here we have 7 positions. We have epsilon, we have L, we have LL, we have LR, RL, RRR. These are the 7 positions we have here. And for every position we require some equations. So if you have a position that still has successors, so it still has such an exit, then the rule is that this xp prime here, so let's mark this in colors, this here is green and this here is blue. What you want is this green equals this blue. Because here what you do is you insert p equals epsilon, and then for p equals epsilon you get the equation that what you exit this SCC with is supposed to be what you enter the left SCC with. And then the same equation tells you that from here you are supposed to go here and these two variables are equal. So you have equality between these two and you have equality between these two variables. And well, similarly here this guy is supposed to be equal to this guy. And actually, yeah, that's the only 3 nodes with successors. Now symmetrically, of course, you have the other thing on the right hand side. This output guy and this output guy and this output guy are each restricted. Namely, they are supposed to be equal to this and this, this and this. So specifically, we have y epsilon equals y right. This is the case where we insert p equals epsilon. We have yr prime equals yrr. That's the case where we use p equals r. And here we have equality between these two by using p equals l. And like how you should view this equality is going back up through the tree. So really how you should think of this whole thing is this whole thing builds a path that goes like this. Woo, 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 woo. And you walk around and you walk around and then you come back up. And now if you walk this path, then what you want is you want to understand the change of the counter values as you take this path. And this path is not some illogical thing, but this path is actually very logical. This is what happens if you look at the yield of the tree. This is you traverse the yield of the tree from left to right. And this is the yield of the tree is important because that's where the non-negativity conditions come in. So this is the situation that you want. Okay. And then, well, the second equations, these were equations where you go up, while these equations here, these were like equations where you go down. But overall, that's just equations where you put values from like one SCC to the next in the obvious way. More interesting is what happens if P is not a successor. So otherwise meaning P is not a successor. P without successor. P without successor. Then what happens? Well, if you don't have a successor, so this means if you are one of these guys, then what's supposed to happen? Well, what's supposed to happen is the obvious thing. You want the Z run from this green guy to from these blue guys to these green guys. Of course, I just write here there is a Z run. This is where I like slightly assume that you have some understanding of VASS. Like at this point, this is just a normal VASS. Like this does not have an exit anymore. So this does not have any non-linear rules anymore. This is just a normal VASS. Accordingly, I can just say, okay, there is a Z run from this left guy to this right guy. Somehow. Or, well, actually, well, you can even simplify it slightly and, well, since I used here two variables, you can even say just that the exit rule goes from here to here. Like, so this SCC has some rule that goes like A goes to +2 or something, like some exit, and you want that this exit applies to these two guys. Like, you can even do this because well, I simplified in this specific case. But really, just think of there's supposed to be a Z run and you're going to be well off. This is like probably the best thing. Okay, so this is what we want to have at these situations. What do we want to have as relation between these guys and these guys? This is arguably the most interesting. What's supposed to hold between these? Well, remember we want to describe the situation that there is a cycle or a context S goes to W prime, and we want to describe where W starts and ends and where W prime starts and ends. And so if W say starts at 5, ends at 3, and here we have 7 goes to 8, then we would describe this as the pair 5 S 8 goes to the pair 3 S 7. So we describe the input, we put the original input as the first element of the first triple, we put the original output as the last element of the last triple, and in the middle we put the non-terminal. And the same way, this the output after applying W, the input after applying W, we write as the new input, and the output after like reading W prime backwards, we write as the new output. And now we don't want W and W prime to be executable, we just want them to have the correct effect. And this is written here by, here it's actually Z reachability. We want to have Z reachability from here to here. Again, this is a cycle. And remember, we have an almost linear grammar. In an almost linear grammar, every rule on a cycle, every rule on a cycle is of the form A goes to W, A W prime. This is literally the definition of an almost linear grammar. So this means that, again, this when I say here Z reachability, this is just Z reachability in a VASS. So for this I can just describe, give a list of equations. Okay. I hope this was not too fast, but this equation just makes sense. Like this is describing the context in the obvious way. And well, I just marked it here for this one SCC that I want this green goes to blue. But of course, this is supposed to hold for all positions. So this is also supposed to hold in these SCCs. Yeah, well, it's supposed to hold in all 7 SCCs. I did not mark them in any logical order. Don't pay attention to the order I just did. It's probably going to negatively affect you. Okay. And then finally, well, I mean, this is kind of also logical, but if you look at this situation here, this was the one location where I had not stated it yet. But whenever you are in this situation, then you want that that these two are equal. So here, if you have some position, then YPL is supposed to be XPR. So here we have, for example, P equals L. If you take P equals L, then you want here YLL equals XLR. We have a similar instance here. If you take P equals R, then you want that these two are equal. Again, this is similar to the first two rules. We just want to propagate the numbers correctly around the tree. The actual computation happens in these two steps. You want the Z run from this to this because you are in the lowest SEC, so now you are actually a VASS, and you want the Z run in the Z cycle in this VASS. Again, this is a VASS because we are almost linear grammar. Yeah, and then finally for this last rule, there is one more instance. If you take P equals epsilon, then you want this guy to equal this guy. And again, this is not illogical, but if you think about the path I drew before, well, the path comes up here and then goes here. And when it goes here, it does not pass through this SSE. It directly goes from YL to XR. So these two are supposed to be equal. So this is all the obvious equations you would put in. It's not some weird equations. They all make sense. The main thing to remember is these two equations and why you can define them. You can define them because almost linear grammars exactly guarantee you that this will be just normal VASS operations. Okay, and then finally, if you want a valid path, then what you're going to put in is that the source and target are supposed to be 0 to the d, both of them. Right, so this should not be complicated, but I want to start the first SEC with 0 to the d and end it with 0 to the d. Now, this should be mentioned, but this is essentially like multi-dimensional borrow-invest scheme. Like the reason I explained the borrow-invest scheme before is if you try to generalize this to more dimensions, then really this kind of integer linear programming and its solutions, this is what you want to express. Like you want to express, I have 0 money here, I borrow myself money 5 times, the 5 times I now have at the next SEC. Then now I take a cycle where I end here with 0, but in exchange I have here, well, still 0, but here I have 10. So if you think about it, there was this rule, a goes to -1 a plus 2. If you use this rule, then, well, what's the context you create? Well, you have 5 here, you have 0 here. You are going to have, because this says or epsilon, you are going to have 0 here, and you are going to have 10 at the end. So for this borrow-invest scheme, you would have 0, 5, 5, then here you have 0, 0. Then finally your borrow actually gives your money back. You have 10 here. Now you enter the next SEC with 10. Then again, you do the same borrow-invest scheme. You go here to 0. You have 0 here. But in exchange, you get your money back here and you have 20. And now when you put these two to 0, what you also did is you caused all these variables to be 0. Because now you cannot actually do anything down here, essentially. Or, well, in that example, these variables did not exist because the grammar ended, but like you can imagine it. So this is perfectly valid to just not do anything below. And the main thing is like kind of, you choose like an anti-chain of non-terminals where you want to invest your money. And in this case, you chose these two locations to invest your money. Now you get back here with 20, and you have to pay back 3 times what you borrowed at the start. So here I borrowed 5, so what I have to pay back is I have to pay back 15, so this means here I go to 5. Yeah, and then, well, now you could say, okay, this is not a solution because I ended with 5. Well, as explained before, I could have just like borrowed less money here. So here I could have just said, okay, 5 here, and then left 5 here all the time. I would have been here with 5. I would have gotten less money back. I would have been here at 15. Then I would have been at 15 here. And so I would have ended with 0. And so I would have had a solution for this ILP. And in general, whenever you have a run, then it's in particular a solution of this ILP. Because you can take the values it enters and exits every SEC at, and these will be non-negative, so you can use them for these n-valued variables. Okay, I know that the ILP took a lot of time to define, and I know that for some of you this will probably have been boring, but I think this is very important, like understanding this kind of structure of the context and how they are supposed to lie inside each other. Like, once you understand this, like the rest of GVAS will become a lot easier. But if you don't properly understand this ILP, like there will be a limit to how much you can understand of the rest of the algorithm. Okay, good. So there's a sufficient condition for reachability. Well, now the correct one for the almost linear GVAS. So we take an almost linear GVAS, we assume it has a pumping cycle, and we assume that it has, so what's this abbreviation? This stands for full support homogeneous solution. And what is a full support homogeneous solution? Well, to explain this, let's go back to the ILP. So whenever you have an ILP and you write this in the form AX equals B, which is essentially what we did when I wrote this here, like, oh, well, it's not quite this form, there are variables on the right, but you can write this in the form AX equals B. And then the homogeneous ILP is AX equals 0. And the full support solution means a solution where every variable is greater than 0. And because this like led to confusion many times, this in particular means all of these are supposed to be greater than 0. Like not just how often I use the productions, which is a little bit hidden in this Z reachability thing. This of course has variables for how often the productions are used. Not just the production variables have to be greater than 0, but also these entrance and exits variables, also all of these I want to be greater than 0. Well, with the exception of these two, these are constants, right? These are not supposed to be greater than 0. These are greater than 0. Yeah. And well, if you wonder what happens if some of these variables are say bounded and say the only solution is 5, well, there is a step that we then have to do in the algorithm for this. It's like later. Okay. So a full support homogeneous solution means that the homogeneous ILP, remember this means the ILP with AX equals 0, this ILP has a solution where every variable is greater than 0. And then finally what we need is we need a Z-run. Well, again, I write this as the last condition. Some people would write this as the first condition. It's obvious that we need it. And then we claim that there is a valid path. Okay, so why would this be true? So step 1 is to analyze what do homogeneous ILP solutions even look like. Let's simplify this slightly and go to this situation. And okay, what does a homogeneous ILP solution look like? So a homogeneous solution, well, okay, maybe I shouldn't have hidden this Z reachability thing. So when I say this Z reachability from x epsilon s y epsilon to x epsilon prime s y epsilon prime, what this means is that I have what is called the Kirchhoff equations and the effect equations. Well, this is one of the situations where I assumed a little bit of knowledge about VASS. So what's these two equations? Well, the effect equation should be kind of obvious. I want to have a cycle S goes to W S W prime, where W has the effect x epsilon prime minus x epsilon. And W prime is supposed to have the effect y epsilon minus y epsilon prime. No, it might look wrong because the primes are the other way on the right hand side, but remember we're thinking W prime is like working towards the inside. Okay, and if you want such a cycle, then cycles are characterized by what is called the Kirchhoff equations. You can forget about these really. Like when we say homogeneous solution, think of it as there is a cycle. It's literally saying the same thing. So homogeneous solution means there's a cycle, and then the main equations we have with this arrow z means that the effect is supposed to be correct. Okay, so what does this mean now if we say we have a full support homogeneous solution? Well, this means that, well, there is a cycle S goes to W epsilon S W epsilon prime. There is a cycle A1, well, A1L goes to WL A1L WL prime, and A1R goes to WR A1R WR prime. So just to understand and just for me to explain the naming scheme, here I always write the P, the position. I write the position P here. And then the left hand side is non-primed and the right hand side always has a prime. And well, the non-terminals just have certain names. I mean, the non-terminal names are probably not optimal here. But okay. And now what's the main point? So what does it mean to be a homogeneous solution? Well, if you think about what these cycles are supposed to do, well, you are going to execute this word in the order W epsilon, WL, WL prime, WR, WR prime, and then W epsilon prime. And what homogeneous solution tells you is that, in particular, these variables here, all these variables are greater than or equal to 0. I mean, they are variables. So, and we consider ILPs, so equations over n. Since these are greater than or equal to 0, what this means is, after you execute this word, you are greater than or equal to 0. After you execute this word, you are greater than or equal to 0. Here as well, greater than or equal to 0. Here, greater than or equal to 0. Here, greater than or equal to 0. And, well, at the start and end also greater than or equal to 0. So it's only in the middle of a word that I could go negative. Okay? Importantly, in the middle of a word I could go negative. So say W epsilon could be -1 plus 1. This is a perfectly fine word. Because we're just talking about ILP solutions. The ILP solution does not talk about the order of the word at all. It just talks about the effect. So we know that at these different checkpoints we will be greater than or equal to 0. And now, why did I talk about this so explicitly? Well, what happens if we use an ILP solution n times? Well, if we use this ILP solution n times, then what we're going to do is we're going to have the word W epsilon to the n, WL to the n, WL prime to the n, WR to the n, WR prime to the n, and W epsilon prime to the n. And now, well, what do we know? Well, if you write this out here, this is a long sequence of W epsilons, right? Well, the point is, in this very long word, there are now 6n locations where we know that we are greater than or equal to 0. Why? Well, we don't just know that we are greater than or equal to 0 here and here. We also know that we are greater than or equal to 0 here and here in the middle locations. So just to like mark it here, this was like before and the end of the n times, but not just there. Actually, we also know that in between these arrows, so after every one of these instances, we will be greater than or equal to 0. If you think about why this is, well, in VASS there is a lemma that if you can use a cycle once, like if you have some source S and this goes by using a cycle n times to t, well, this is the case if and only if S can fire the cycle once and T can be used by using the cycle once, and T minus S is the effect of is N times the effect of rho. This is essentially like the kind of thing we are using here. But so here we know that at all of these locations we are greater than or equal to 0, at all of these intermediate locations. Why is this useful? Well, this means that think about at which value can we use this word. And now, instead of thinking about this like for a long time, and just think about what I just told you. Essentially, I told you that after every constant amount of stuff, so something that does not depend on n, you know that you are greater than or equal to 0 on n. So there are only constant length runs where you don't know that you are greater than or equal to 0. So the answer is, at which value can we use this word? Well, some constant in terms of something that is constant in n. Like if you want a specific thing, it's like maximum of the hurdle of all the words. But like this is a horribly like complicated way to think about it. Like really the main thing is it's constant in terms of n. The formal thing is it's something like the maximum of the hurdle of all these like component words. It's the very simple important thing is it's constant in n. This is the thing we will be using in a moment. So repeating a homogeneous solution very often actually means that you can still use it at a very small word. Okay, so now how are we going to do this in the proof? Well, remember we have a cycle. But what we need in order to get some kind of run is we want some kind of different derivation. So some kind of cycle that cancels the pump. How do we do this? Well, the pump that we have in the top SCC, S goes to up, S down. Well, just create a homogeneous solution greater than this one. Remember that we have a full support homogeneous solution. So in particular, there is a homogeneous solution using every production more often than the cycle. And now this is the main trick. So we have our H, and here we have our pump. And now H uses every production more often than the pump. So what do? Well, we define diff by just taking H minus pump. You might say, but how can I subtract the derivation? Well, this is where again the Kirchhoff equations come in. And when you think of a cycle, actually it's just a solution to some equation system. And now if you have a larger solution of an equation system, then you can just subtract these two solutions from each other. And then magically you can again make this into a derivation. Like this is the thing about the Kirchhoff equations. You can think of cycles as being really just solutions from an equation, and so you can subtract a smaller cycle from a larger cycle and get again a cycle. So there is now a cycle diff that goes S goes to W epsilon S W epsilon prime. But remember, diff took a homogeneous solution and subtracted something. So diff, of course, also has parts here and here. So this is just diff epsilon. Diff has also a diff L, which goes, well, from A1L to WL, A1L, WL prime. And it has a diff R which goes from A1R to WR A1R WR prime. Okay. And now you might wonder, okay, how did this help me? Well, let's forget about the Z run for now. What run are we going to produce? Well, we are going to do the following. First, we are going to repeat the pump n times. This causes our word to look something like this. And then what are we going to do? Well, in the middle we are going to do the homogeneous, the difference n times. If we do the difference n times, then we know that in total we did not cause any effect. So what we do is here we do exactly what we analyzed before. W epsilon to the n, WL to the n, WL prime to the n. It's not WR yet, we are still in the left SEC. Then WR to the n, WR prime to the n, and finally W epsilon prime to the n. This is the word. This I claim is well, I have not inputted the Z run yet, but this is essentially the run. So why does this not go negative? Well, at this location we have a value greater than or equal to n, and here we are also greater than or equal to n. And now comes the analysis we did before. This word has constant hurdle. So this means there exists an n where this word there exists an n such that this is a run. Well, I have not put the Z run in, but you can now imagine, okay, I have to like insert a little bit of garbage everywhere here in this run. Like there are a lot of locations here in this run where I will insert a lot of garbage, but still, this is a constant amount of garbage. The Z run is constant. So if I insert this constant amount of garbage, that is the Z run, then, well, this still only has constant hurdle in the middle, and I'm still linear here and here. So in total, okay, now of course this is stupid. This has constant hurdle, and the point is this is linear. And so in total, if I construct my word this way, taking the pump n times, doing this homogeneous solution, and the Z run somehow inserts itself in the middle, then there is an n such that this is a run. And this proves the theorem. If you have an almost linear GVAS with a pump and a full support homogeneous ILP solution and a Z run, then in fact there is a valid path. Okay, so where do we stand? Let's repeat what was the algorithm. So the algorithm was as follows. Now we actually use the condition that we just invented. We need a cycle, a pumping cycle, we need a full support homogeneous ILP solution, and we need a Z run, and then there is a path. So what does the algorithm now do? Well, as always, it inserts the GVAS we are interested in into the work set, and then continually we check whether the sufficient condition is fulfilled for everything in the work set. If it is, then we return whether we have an empty work set or not. Otherwise, we remove G and put everything that is smaller into G. Some smaller things that I have not defined yet, but this is now the next thing we are going to do. So let's make an important observation here. The sufficient condition is in fact decidable in exponential space. So this part, in general, we have to worry about it, but here in almost linear grammars, we don't have to worry about this. This is simply decidable in exponential space. Why is this? Well, here, the important thing is cycles in an almost linear grammar have only productions of the form A goes to W, A, W prime. So you can make this into a 2D VASS, where you take a transition A and then you go with the operation W prime reverse to A prime. Now this is just a normal VASS, and having such a pump in the grammar is equivalent to having a pump in this 2D VASS. And well, pumpability in a normal VASS is decidable in exponential space. This is another one of the locations where I assume you are a little bit familiar with VASS. So this is by Rakov from 78, that you can actually decide coverability in exponential space. And this is the algorithm we are going to use here. And then, okay, you might say the other two conditions also need deciding. When Z-run I have already talked about. Z-run is not a very complicated thing. It's very easy to check. This is in NP, in fact. And, well, full support homogeneous ILP solution. Here we can argue semantics whether this is NP or NEXP. So, well, it is NP in terms of the... okay, why would it be NEXP? For this, let's go back to the very start of this presentation. So here, if you think about this grammar is very small, but we unfold it into this very large tree that's exponentially larger. So if you store your grammar in this way, then the ILP has exponential size. And if the ILP has exponential size, then this of course means that you will not be able to check this ILP in less than NEXP. But, well, this ILP might be easier, like you could argue that maybe it's easier than NEXP, but NEXP would be the intuitive upper bound. On the other hand, if you store your whole grammar like this, so you have already converted it, then it would be NP. But either way, it's an easy condition. Okay, so this is also below X space. So really the most difficult condition is this topmost one. And this one I have just argued is in X space by Rakov. So we can actually implement this while loop. And then the only question is, can we implement this thing smaller? Or what does this smaller function do? Well, that's what we're now going to do on the next slides. So first of all, in order to make anything smaller, we need to first say what small means. So we need to define the rank of a GVAS, and the rank will be using what is called the cycle space. So if you have some non-terminal A, then the cycle space at this non-terminal is defined as follows. So you take all cycles A goes to W, A, W prime, and you consider the vector space, I did not write it, but this is contained in Q to the 2D. You consider the vector space spanned by pairs effect of W, effect of W prime. Or if you want to think about it, you can also say, and we are thinking about the cycle space in the 2D VASS. So remember that when I decided the coverability on the slide before, I kind of viewed the whole thing as being a VASS with like 2D counters. This is again one of the instances where we do this. The cycle space is defined as if we are a VASS with 2D counters. And then, well, using the cycle space, we define the dimension of this non-terminal as the dimension of the cycle space. And then the rank of the grammar is you take the sum over all the non-terminals of, well, I write it as ordinal. You can also think about it as vectors in ND. If you think of it as vectors in ND, then omega to the dimension of A means you have here a very long vector, and you have a 1 at the coordinate corresponding to the 1 in the coordinate dimension of A. or +1, and like you can think about it from which side you add, but like the point is higher dimension means you are way larger. Like if you have a dimension 1, then your rank is omega. But if you have 5 non-terminals with like dimension 0, then you have rank 5. So this again, just like in VASS, this ensures that if you have a single non-terminal with a higher dimension, then this is worse than having arbitrarily many non-terminals with smaller dimension. So as a few examples, if you have some acyclic grammar, then you get the number of non-terminals as the rank, because, well, you don't have any cycles, so every single non-terminal has dimension 0. Like, duh. Uh, if you have a non-terminal with 1 cycle like this, then this has a dimension 1, and so its rank is omega. And now you might ask, why do I add this example? Because I want to explicitly say we consider pairs. And considering pairs means that even though here the sum equals 0, this still has dimension 1 because you're in the pair vector space. This is still the vector space generated by +1, -1. This is not the vector space generated by the sum of effects, which would be the 0 vector space. No, this is the vector space generated by the pair +1, -1. So this has dimension 1. And similarly, this grammar here, this is a 1 GVAS, but nevertheless, this has dimension 2. So this is to say, even if you just have a 1 counter GVAS, a 1 counter GVAS can still be 2-dimensional. There's no problem with a 1 counter GVAS being 2-dimensional. This is just fundamentally how this definition works. Okay. So this is the rank, and so now we're going to claim that this is decreasing. And so just to explain what does it mean that this decreases? Well, this means that you take a non-terminal of dimension, you take one a non-terminal of dimension k, and you are going to produce it by a ridiculous number, say 1 million non-terminals of dimension k minus 1. And then if you do this, then this has decreased the rank. Of course, you might say this produced a very large object. Well, this is why the algorithm will be Ackermann. Okay, so decomposition number 1, what happens if you don't have a pump? Because remember, which conditions did we have? We had the condition that there is supposed to be a pump and these two ILP-based conditions. Now, if you don't have a pump, then the solution is the same as in VASS, in case you know how it works in VASS. And the effect is that in the corresponding 2D VASS, some counter is bounded. Here we have a bounded counter. Then this actually means that something is bounded in the GVAS. So what we're going to do is we're going to store it in V here means non-terminals, right? Not VASS. V is the set of non-terminals. So we're going to store it in the non-terminal. Simple example. Say you have this grammar, that the main point is you have 2 non-terminals. This is the first SCC. It just exits immediately, but before it produces value +3. And then you have this SCC. So this is like 2 SCCs. You have first S, and then below it you have A. So in this case, you will start the SCC A with a value 3, but in SCC A on the left-hand side you cannot change the counter. You cannot increase the counter on the left-hand side. The only thing that changes the counter on the left-hand side is this production. So because this is the only production that changes the counter on the left-hand side, the counter on the left-hand side is bounded. So since the counter on the left-hand side is bounded, this means we have to store the counter in our non-terminal. The result is that we are going to have non-terminals S, A3, A2, A1, and A0. And while the productions are as you would imagine, if you are currently at A3 and you apply this production, then you are going to go to A2. Or, well, you do the -1, of course, and then you go to A2. And similarly, if you are at A2, then you apply the production and go to A1, and so on. Well, it's literally the same way you would do it in VASS, but the reason I take this example is because of these right-hand sides. I want to make it clear all of these non-terminals still have the rule A3 goes to A3 plus 1 or A3 minus 1. These rules still exist. They are not deleted. So if you think about it in terms of the tree structure, you have S, you have A, and you have your x epsilon prime, y epsilon prime, y epsilon, x. Well, I guess now it does not make sense to call it L, but let's call it L. XL, XL prime, YL prime, YL. Then what happened is, well, first of all, you expanded this into being now 4 non-terminals. So now you have here A3, and then you have A2, A1, and A0. But more importantly, what happened is these variables here, these now have fixed values. But on the right-hand side, you don't have fixed values. On the right-hand side, you continue to have your counter. It's only the left-hand side where your counter is bounded. And hence only the left-hand side where your counter does not exist anymore. And so now in the new grammar, if you think about it, remember the cycle space. Well, the cycle space here of A was 2D. Namely, it was two-dimensional. Why? Well, the cycle space was generated by 0 plus 1. This is from here. This is a cycle which has 0 on the left but plus 1 on the right. And it's generated by this other one, minus 1a. Minus 1a means minus 1 and 0. And together these two of course have dimension 2. But now in the new grammar, what we produced is, well, every cycle has fx 0 on the left. So this means the dimension is now less than or equal to 1. In fact, it's exactly equal to 1. Because, as I said, the right-hand side still exists. The right-hand side with this plus 1, minus 1, this still exists. The cycle space still has dimension 1. But it's no longer dimension 2. And yeah, I will actually leave it at this. Like, you can think about why does the rank decrease. In general, well, I explained it here, but the point is cycles with non-zero effect on the bounded counter are killed. Okay, and now, well, there is one special case. What if there was no such cycle? Like, this is a question. You might ask me, what if there was no such cycle? Well, this is actually kind of a stupid question, Well, because then the answer is the counter did not exist to begin with. So we would not have made this decomposition because the counter was like already removed before. Like if there is already no cycle that has a non-zero effect on this counter, then this means the counter was already removed before. It was a counter we had already handled before. Then we didn't do this decomposition. Like essentially, if you want to think formally, what this means is the algorithm stores which counters it still has to handle. Which counters still have to be handled. And specifically, there is a concept here that is called a rigid counter. And just like in VASS, these are like special things. If you have a rigid counter, then you know that you don't have to care about this counter. Like you view your VASS as having one counter less. You just kill this thing. This is like a minor cleaning step that you have to do. This is one of the reasons why this algorithm is not so easy. Like most of the steps have like non-trivial sub-steps where you need to imagine, hey, what if this stupid case happens? And then I need to tell you, well, the counter was already removed before, meaning it was rigid. So actually we would not have done this decomposition. There was a separate step that like would have dealt with the situation. This is the complicated thing about the VASS reachability algorithm. And this is kind of what we're building here. But okay, I just try to like give you the intuition. Same as in VASS, take a counter that is bounded, store it in your non-terminal. We have now removed non-zero cycles. But importantly, you have to remember which counters are rigid. Because otherwise, if you try to remove the same counter again, you have not decreased the rank. Okay, so decomposition number 2. What if a production is bounded? So why this? Well, remember the second condition was this full support homogeneous solution. And well, if you don't have such a thing, then this means that there is there is like something that you have to know about ILPs. If in an ILP there is no full support homogeneous solution, then this implies that some variable is bounded. Like, I will not check this here, I assume you know this, but this is what we're now going to use. So if there is no full support homogeneous solution, then this means that some variable is bounded. And now we're going to do a decomposition depending on which variable it is. Or, well, okay, let's make the even more obvious thing. If you don't have a Z-run, then you just reject. So this is the last thing we have to check. What do we do if a variable is bounded? Okay. So the more interesting thing, like it's also possible that some like variable of what value will you have somewhere is bounded. So if one of these x epsilon, y epsilon, etc. thingies is bounded, then like this is similar to before, this is some cleaning step. Like I don't want to go into the details of this would go way too deep. But there's some cleaning step that takes care of if this variable is bounded, then I change something in the structure, but essentially I'm not doing much. I just write the number there. The more interesting thing is what if a production is bounded? Or if you think in terms of the VASS, this would mean some transition is bounded. Then what we're going to do is we're going to enforce exactly a given number of uses of this production. And well, importantly, this remains almost linear. So let's give an example of this. So, well, actually it's exactly the same we had before, but now I removed the right hand side for simplicity. Well, if you have this kind of thing, then this rule here is bounded. And so the fact that this rule here is bounded means that you now create, just as we had before, you create the structure S, A3, A2, A1, A0. And well, you remove this production from every SEC. And well, we have already checked before that this actually decreases the cycle space. Okay, well, but of course we want to be a little bit more formal. Why does this remain almost linear, you might ask? Well, think about it as follows. So, okay, so what is the condition for almost linear? The condition for almost linear is every production remaining in the same SEC something. Every production which does not leave every production which does not leave SEC P, which does not leave the SEC something. Like, I mean, the exact something is not important, but like, this is essentially the point. So now, if I want to check that this condition still holds, I have to take myself a production in the new grammar which does not leave an SEC. Well, in the new grammar, if a production does not leave an SEC, this means the production is not P. Well, actually, okay, if I take a production in the new grammar, so productions P prime and P prime not leaving an SEC afterwards. Well, this is contained in the same before. Like, if you have a production which afterwards does not leave an SEC, then in particular it does not leave an SEC before. So I can use that my grammar used to be almost linear, and I know that the corresponding production is was of the form. So this means production was of the form A goes to W, A prime, W prime. And now this is the type of shape that's just preserved, so the production is still of this shape, but now it will be like written something like this: A K goes to W A prime M something. But still this is almost linear. So almost linear was preserved. The other thing I have to check, well, why do we in general preserve the rank? Well, for those of you familiar with how this works in VASS, actually there is a detail here that I have to mention. The important thing is you have to remove all bounded productions at once. This is necessary to reduce the rank. And just to give you a quick intuition why this would work, well, so this means that afterwards only unbounded productions remain. Unbounded productions, and so unbounded productions kind of corresponds to unbounded effects. And now the point is, this is essentially what we have to prove. Like, no linear combination of unbounded stuff is bounded. This is kind of like well, if you think about it, actually this grammar kind of illustrates it. So if something is bounded, then this actually means that some kind of direction and space is bounded. Like there is a direction and space such that you cannot go into the opposite direction. Now, if you remove everything that can even slightly go in this direction, then now, well, you have removed it. But really, this is the type of thing where like you should once write the proof yourself and then you really understand it. If somebody shows you the proof, it will just take a while. So I would recommend you like exercise, try to write this proof that rank goes down. Write proof of rank degrees. If you are really lost, then you can look at like Leroux and Schmitz in 2019 had a paper where they do this for VASS, and essentially the same thing works here. Well, this paper was like putting reachability into a primitive recursive. They essentially also invented this cycle space rank. So yeah, the proof essentially is the same. It's the same reason. A linear combination of something unbounded does not give something bounded. Okay, so now this is the whole combination. So in total, we have now actually shown that reachability in almost linear is an Ackermann. Well, specifically we have shown f2d plus something. It's plus something because the rank was less than the rank was less than omega to the 2d plus 1, and there's a little bit of like stuff involved with the fact that we have X space for a single decomposition step. Like, it doesn't matter. It's something like F2D. And you can in fact analyze it to be exactly F2D. Like, if you improve the algorithm slightly, then you get exactly F2D. Okay. Good. With this, we have done almost linear. So now I should tell you what we're going to do next time. Well, next time we are going to look at how to extend almost linear to deal with thin. So next time we're going to extend this to the class of all thin GVAS. For this, we are essentially going to look at the ILP, and we're going to see how to make the ILP work in presence of like non-terminals on the sides. Like, this will not be too much of a problem, but this is also not too trivial. Okay. But nevertheless, like, if you understood today, then next time will become a lot easier how to deal with thin. Okay. So maybe one thing I should say is today's results are in fact highly non-trivial already, because if you can solve reachability in almost linear GVAS, then in particular this means you can solve reachability in VASS. And this algorithm is supposedly very complicated. Well, I always thought that the ideas are not that hard. It's really just 3 ideas you need: sufficient condition, pumping cycle, and difference cycle. But, well, yeah, I admit that if you try to write the syntax of the algorithm is pretty complicated. Okay. And, well, what I want to end today with is some interesting open problems. So the first one is, if we have, I just told you that the algorithm is F2D. So the question is this actually necessary? Or is there maybe a reachability algorithm that works in FD plus something? This is actually something I'm currently thinking about, and it's not so easy. In particular, there's already a very interesting case. What is the complexity of 2-counter almost linear GVAS? At the moment, I'm very heavily trying to put this into tower, and it's kind of fighting me. So if I manage to put this into tower, then I'm pretty sure I also get it for thin. Like, there's essentially, for 2 counters, there is not yet a difference between thin and almost linear. But somehow it doesn't want to work. Like, these almost linear 2 GVAS, they are fighting me on every single side. But so this is one of the open problems I would very much recommend. If you are at all interested in GVAS, like, how complicated are 2-counter almost linear GVAS? It's a situation that you can explain to people. Because it's essentially like a 4-VAS. So, well, that's the point. We analyze it like it's a 4-VAS. But is it really a 4 VASS? Is this really the best you can do? I mean, actually you just have two counters, right? Is it really optimal to analyze this like a 4 VASS? Well, it's a question, and this is one of the things I leave open here. But yeah, I hope I hope I could convince you of the reachability for almost linear. And I hope that you're going to tune in next time when we're going to turn that into a reachability algorithm for thin. Yeah, and with that, I end today's video. Thank you for listening.